In this video, we're going to talk about particles known as resonances and a particle property known as strangeness. Yes, these are real names. Gotta love particle physics. So starting with resonances, there are some particles that are not around for very long at all. We're talking about on the order of 10 to the negative 23rd seconds. Now, at that short amount of time, even with our best detectors, we can't see these particles, but we can see the particles that they decay into. And so, yes, we infer from the decay products their existence. By the way, these are usually particles produced by the strong force. They decayed due to the strong force. Basically, the stronger the force that mediates the decay, the quicker the decay is going to happen. So the weak force is going to give you decays that take a while, so to speak, relatively. Then the electromagnetic force, and then the strong force. So particles that decay by each of these, those that decay by the weak force are going to be around longer. Those that decay by the strong force are going to be around for a short amount of time. Now, they're all for a short amount of times. We're talking about relatively long and short here. Anyway, so again, we have to infer these, and a lot of people don't like that. I will mention that they have very strict statistical evidence needed before they will agree that there is a particle there. There's what they call the 5 sigma confidence level. 5 sigma refers to 5 standard deviations for those of you with some statistics background. This is equivalent to a p-value of 0.12345 and then a 3 at the end. Typical p-values for other scientific endeavors are like 0.05 or sometimes 0.01. So to kind of make up for the fact that they're inferring these decay products, they need a whole lot of confidence that what they are seeing is not a fluke. And before you get too worried about this idea that we have to infer their existence without actually ever seeing them, this is not all that uncommon in science. I mean, we are pretty sure that fusion is what powers the stars, including our own sun, but we've never actually observed that. We haven't gone to a star and taken a core sample and seen nuclear reactions going on there. And if you get really philosophical, we don't really observe anything directly, so, you know, you can kind of have issues with all kinds of things if you want to. All right, moving on to more stable ground. Here's how we do these calculations for these particles that we can't see. So here's an example of one of the very first resonant particles or resonances that was ever found, and it's known as the delta particle. So if you shoot a beam of positive pions at some sample with a bunch of protons, then you basically get the pions out and the protons out. Okay, well that's nice, very exciting reaction there. But interestingly enough, if these pions have just the right kinetic energy, so you could shoot them faster or slower, and we're measuring these kinetic energies in mega electron volts because we like to measure everything in that, right? Well, what happens is around certain values of kinetic energy, these pions don't go straight through the proton samples. They get scattered off at different angles. So here's your pions coming in, and instead of hitting your detector here, you know, maybe you've got a detector going around here, and they end up hitting at angles, you know, they didn't go straight through. So what we see is we don't just see that turn on at one specific energy and then off at the next. You know, we don't have a sharp peak that would tell us the kinetic energy needed to get this deflection. It kind of gradually peaks up and then goes down. So what they think is happening is that you are producing a delta particle momentarily, and then that delta particle is decaying back into the pion and the proton. So the idea of this energy here, this was the kinetic energy required to produce the pion, sorry, not the pion, the delta. So we think that this is close to the mass energy of the delta. So the width of this peak here gives us an estimate of the mass of this very, very short-lived particle that we don't even see, but there's some evidence that something was going on. So we use our good old uncertainty relation. We saw this in the first video. And we say the uncertainty in our energy times the uncertainty in our time is equal to Planck's constant over 2 pi. And what we can do is we can look at this energy uncertainty, because we don't know exactly how much energy. It was somewhere in this range. And that's going to give us an idea of the average lifetime, the uncertainty in the time that this thing existed, which is its lifetime, for the given resonant particle. We call this resonance because if you have like waves of certain frequencies, if they're the resonant frequencies, you'll get peaks in those waves rather than having the waves die off. Not too important, but all right. So if I rearrange this equation here just to solve it for delta t, I get something that looks like this. Now you might have remembered we used this equation before and we derived a different equation. We ended up with something that looked like this: mc squared equals hc over 2 pi d. Okay, so don't get these equations confused. I mean, they're derived, they both come from this. I mean, this is just a simple rearranging. But for the e, we plugged in mc squared, and for the delta t, we plugged in d over c, and then we moved it to the other side and all that. Anyway, just be careful not to put a c up here in the numerator is really all I wanted to say about that. All right, so if we know the width of this peak, and let's just assume this is about 100 MeV here, from there to there, then we can get an estimate of the lifetime of this particle. So we plug in Planck's constant, 6.6 times 10 to the negative 34th joules times seconds over 2 pi, and then we've got our energy width here, which is 100 mega electron volts. Now we've got MeV down here, which are energy units, joules up here, so we have to do a conversion factor, which was 1.6 times 10 to the negative 13th joules per MeV. Squeeze that in there, joules go away. We're going to end up with seconds, and this is 6.6 times 10 to the negative 24th seconds, which is fairly close to the lifespan of a delta particle. Okay, so there's a number of particles that do this. This is essentially how, well, more or less how they figured out the mass of the Higgs boson, was looking at things like this. We didn't directly see a Higgs boson. We'll talk more about that later. All right, on to strangeness. What a wonderful name. So we had some other particles, the kaon, the lambda, and the sigma, that when we first discovered them, we noticed that they were always produced in pairs, but we didn't know why. There seemed to be no good reason. There were a number of other options of things that could have been produced in these reactions, but they weren't. It was always seeing these things in pairs, and so to explain it, we introduced this new property called strangeness, which is given an S. And let me go to an example of a couple of interactions. So this one up here, this one happens. So check, yes. This one never happens. And there's no reason, or at least prior to defining this quantity of strangeness, to see why that would be. This reaction here wouldn't violate baryon number, wouldn't violate conservation of energy, wouldn't violate lepton number, wouldn't violate anything unless we invent a new thing that it does violate. So let's look at how these numbers work out. Over here on the initial side, let's look at baryon number, lepton number, and charge. We'll use Q for charge. So this guy is a baryon and that guy is not, so we've got baryon number of 1. No leptons over here. This guy's positive, it's a proton, and that guy's negative, so our charge is 0. Okay, over here, baryon, lepton, charge. Kaons are not baryons, lambdas are, so we have a baryon number of 1, lepton number of 0, charge of 0 over here, because these are both neutral. So that all works out like it should. Okay, but over here we more or less have the same thing. So we have baryon number of 1, obviously it's going to be identical to what it was before. Over here, the neutron is a baryon, none of them are leptons, and the net charge over here is still 0. So we didn't understand why this wasn't happening. But if we ascribe a strangeness value, and we can add that here, S, neither the pion nor the proton is a strange particle. It does not have any strangeness. The kaon, we ascribe a value of +1 strangeness, and the lambda, we ascribe a value of -1 strangeness, so we get a net strangeness of 0. And over here, the kaon is +1. The neutron, though, has 0 strangeness, so we get +1 strangeness over here, and we started with 0. So this violates conservation of strangeness, which is why this does not happen. This was kind of named because it was weird, and it got even weirder. Let me jump back to this other slide. This last bullet point here, they are created in a strong interaction and decay to strongly interacting particles, but have lifetimes characteristic of the weak interaction. So I mentioned earlier that if they're decaying by the weak interaction, they're going to have longer lives than if they decay by the strong interaction. So we think that they actually do decay according to the weak interaction, but they're always produced, they're created by the strong interaction. Okay, and the weird thing here is that strangeness, I'll just say S, is conserved when they are created because they're created in the strong interaction, but strangeness is not conserved for weak interactions. So when they decay, they actually don't conserve strangeness number, but when they are created, then they do have to conserve strangeness. Pretty weird. This was the first what we call partially conserved quantity, and a few others came along later. So if we jump to our wonderful chart of everything we know. By the way, we're introducing these ideas kind of piecemeal, one at a time, because it's a lot to take in. Shortly we will kind of put the whole picture together. But if you look over here, this S value here is the strangeness. So the gluons, or all the bosons, the leptons, none of those have any strangeness. These guys right here, the kaon particles, all have a strangeness value of +1. The lambda and the sigma particles have -1. The Xi particles have -2, omega has -3, and their antiparticles will have opposite strangeness values. So the anti-kaon will have -1, and these guys will be positive, and so forth.